there's conceivably a way to do warp drive, but it's such esoteric, super out on the edge physics, because technically you cannot go faster than the speed of light.
NASA looks at going to the moon one day and to Mars, and to get to Mars, they're going nuclear.
Elon Musk has just unveiled a game-changing announcement that could redefine the future of space exploration. After years of speculation, rumors, and groundbreaking technological advances, Musk has introduced the new warp drive Starship, a spacecraft unlike anything ever seen before. Could this truly enable travel faster than the speed of light, as depicted in science fiction? The moment we've all been eagerly awaiting has arrived. As the CEO of SpaceX and Tesla, Elon Musk has revealed a development that sounds straight out of a sci-fi novel, a breakthrough that could revolutionize our understanding of space travel. Today, we delve into the details of SpaceX's newly announced warp drive Starship, a marvel that has left the world in awe. This announcement could potentially rewrite the laws of physics and bring humanity closer to becoming an interplanetary species. Join us as we explore what this warp drive entails, how it operates, its implications for the future of space exploration, and its impact on our grasp of the universe. The vision behind the warp drive Starship. From the outset, Elon Musk's ambition has been unmistakable: to make life multiplanetary. Since the inception of SpaceX in 2002, Musk has passionately pursued the goal of sending humans to Mars, establishing a self-sustaining colony, and ultimately transforming humanity into a multiplanetary species. Yet, with current technology, traveling to Mars and beyond remains a time-consuming and costly endeavor. Musk has always recognized that realizing this vision requires a revolutionary propulsion system, one that challenges our existing notions of speed, distance, and energy. Now, he believes SpaceX has achieved that breakthrough. In a highly anticipated announcement, Musk unveiled the warp drive Starship. This isn't merely about accelerating our journey to Mars. It's about reaching the farthest reaches of our galaxy in a fraction of the time once thought possible. But how does this warp drive function, and what enabled SpaceX to develop such groundbreaking technology? To grasp this, we first need to explore the science behind warp drives and their theoretical foundations. Understanding the concept of warp drive. The concept of a warp drive isn't new. It's long been a fixture in science fiction, notably featured in shows like Star Trek. The real question, however, is whether warp drives could ever become a reality. The warp drive idea revolves around manipulating space-time itself to enable faster-than-light travel. According to conventional physics, nothing can surpass the speed of light in a vacuum. But warp drive theory proposes an alternative. Rather than traveling through space at superluminal speeds, a spacecraft could distort space-time by contracting space in front of it and expanding it behind. This would theoretically create a bubble around the spacecraft, allowing it to move faster than light relative to the space outside the bubble. Think of space-time as a fabric. By compressing and stretching this fabric, the spacecraft doesn't actually need to exceed the speed of light. It simply shortens the distance it must traverse. The theoretical groundwork for this was laid by Mexican physicist Miguel Alcubierre in 1994, who demonstrated through his equations that a warp drive could, in principle, be feasible. The major hurdle remains the colossal amount of energy required to create and maintain such a bubble, an amount far beyond our current technological capacity. So, what has changed? What new discovery by SpaceX might make warp drives a plausible reality? The breakthrough, SpaceX's technological leap. Musk's announcement was more than just talk. It included a detailed explanation of the technology behind SpaceX's warp drive Starship. The breakthrough hinges on several advancements: quantum mechanics, exotic matter, and zero-point energy. First, exotic matter plays a crucial role. Unlike ordinary matter, it has negative energy density, which is essential for creating the warp bubble described in Alcubierre's theory. For years, scientists questioned whether exotic matter could exist. But recent breakthroughs at SpaceX suggest they've successfully synthesized small quantities of it in a controlled setting. Next, there's zero-point energy, which is the lowest possible energy a quantum system can possess. Musk has hinted at SpaceX's work on zero-point energy, and this announcement confirms they've developed a prototype engine that harnesses zero-point fluctuations to generate the immense energy required for the warp drive. The synergy of exotic matter and zero-point energy has led to the creation of what Musk calls the warp field generator. This device, central to the new Starship, allows it to manipulate space-time and effectively shorten the distance to its destination. The warp field generator is powered by an array of ultra-efficient fusion reactors that provide the initial energy to form the warp bubble. Once established, the ship can ride this bubble like a wave, traveling faster than light. This monumental achievement marks the culmination of years of research and development by SpaceX's leading scientists and engineers, representing a significant leap forward in space exploration and the future of humanity. Testing the warp drive Starship. Musk's announcement not only unveiled the technology behind the warp drive Starship, but also provided insights into the extensive testing the ship has undergone. According to Musk, SpaceX has carried out numerous tests of the warp drive, both on Earth and in space. The first successful test took place in a vacuum chamber at SpaceX's research facility, where a miniature warp field generator was used to create a small warp bubble. This experiment demonstrated the feasibility of warping spacetime in a controlled setting, showing a measurable reduction in distance between 2 points inside the chamber and validating the theoretical predictions of the warp drive equations. Following this, SpaceX tested the drive in space by launching a small unmanned test craft equipped with a scaled-down version of the warp drive. This craft entered orbit and successfully generated a warp bubble, traveling a short distance at faster-than-light speeds. This achievement proved that the warp drive could operate in the vacuum of space. But the progress didn't stop there. Musk revealed that SpaceX has conducted over a dozen additional tests in space, each progressively more complex and extended in duration. The final test, conducted just weeks before the announcement, involved a full-scale prototype of the warp drive Starship. This test saw the Starship travel to the outer edges of our solar system and back in just a few hours, an expedition that would have taken years with conventional propulsion methods. These tests have been closely monitored by international space agencies and independent scientists who have confirmed the results. It's now official. SpaceX's warp drive is operational and ready for its next phase. Implications for space exploration. With SpaceX's breakthrough in developing a functional warp drive, the future of space exploration is on the brink of a revolution. This new technology addresses one of the greatest hurdles in space travel: the immense distances between celestial bodies. Traditional rocket propulsion would require tens of thousands of years to reach even the closest star systems. In contrast, the warp drive could make these journeys feasible within days or weeks. The distance to Mars, a primary target of SpaceX's efforts so far, could now be covered in mere minutes. This advancement opens up extraordinary possibilities for exploration and colonization. The prospect of human settlements on Mars, the moons of Jupiter or Saturn, or even distant planets in other star systems, suddenly shifts from a distant dream to a tangible reality. Furthermore, this technology could revolutionize our approach to exoplanet exploration. Thousands of exoplanets have been identified, but reaching them has previously seemed unattainable with current technology. The warp drive changes that paradigm, making missions to these distant worlds achievable within a human lifetime. Additionally, the warp drive could redefine our understanding of the universe. It enables us to send probes to the far reaches of the galaxy and beyond, allowing us to investigate phenomena such as black holes, dark matter, and cosmic radiation with unprecedented detail. The insights gained from these missions could dramatically alter our comprehension of physics, cosmology, and the very nature of reality. Potential applications beyond space exploration. Musk's discussion on the warp drive technology goes beyond its implications for space exploration. He hinted at its potential to transform various forms of transportation on Earth. For example, this technology could be adapted for aircraft, enabling ultra-fast travel between continents. Picture a flight from New York to Tokyo taking under a minute. Such a development would revolutionize the transportation industry and bring the world closer together in ways we can barely imagine today. Moreover, the principles of warp drive could impact other fields, such as communication and energy. Manipulating space-time might lead to instant information transmission across great distances or new methods of harnessing energy. Musk also noted the potential applications in medical and scientific research, including advancements in quantum computing, medical imaging, and particle physics. This technology could pave the way for groundbreaking discoveries and a deeper understanding of the universe. The reaction from the scientific community. The announcement of the warp drive Starship has created a buzz in the scientific community. While many are thrilled by the potential of this groundbreaking technology, a considerable amount of skepticism remains. Some physicists are challenging SpaceX's claims, arguing that the concept of a warp drive is still theoretical and that the technology required to create and sustain a warp bubble is far beyond our current capabilities. Concerns also arise about the risks and ethical considerations associated with such technology, particularly regarding human exploration of other planets. On the other hand, many scientists remain cautiously optimistic. Dr. Michio Kaku, a distinguished theoretical physicist, has hailed the announcement as the most thrilling development in space travel since the Apollo moon landing. Kaku, a longtime advocate for the warp drive concept, believes SpaceX's breakthrough might be the key to realizing it. Similarly, Dr. Neil deGrasse Tyson has voiced his excitement about the technology, suggesting it could fundamentally alter our understanding of space-time and the universe. Tyson underscores the need for continued research and experimentation to fully grasp the warp drive's implications and ensure its safe and ethical use. The next steps for SpaceX. Following the successful tests of their warp drive Starship, SpaceX is moving forward with the next phase of development. Elon Musk has announced that the company is planning a series of manned test flights to further assess the capabilities and safety of the warp drive technology. The first manned flight is set to occur within the next year, featuring a crew of highly trained astronauts and scientists. This mission will focus on testing the warp drive under increasingly complex conditions, including long-distance travel and maneuvers near celestial bodies. In addition to these test flights, SpaceX is working on assembling a fleet of warp drive starships, with the aim of having multiple ships ready for interplanetary missions within the next decade. Musk envisions these starships being utilized for various purposes, from transporting cargo and passengers to conducting scientific research and exploration missions. SpaceX is also partnering with international space agencies and private companies to explore the potential applications of warp drive technology. Musk has expressed a strong desire to foster a new era of cooperation and collaboration in space exploration, where nations and organizations work together to fully realize the possibilities of this groundbreaking technology. The future of humanity in space. Elon Musk's latest announcement represents a pivotal moment in space exploration history. The development of the warp drive Starship could fundamentally transform our approach to space travel and bring us closer than ever to becoming an interplanetary species. But what does this mean for humanity's future in space? For Musk, the answer is unequivocal. This is merely the beginning. He envisions a future where humans inhabit and work on multiple planets, exploring the farthest corners of the galaxy and beyond. Musk argues that this future is not only desirable, but essential for humanity's survival and advancement. He has frequently highlighted the importance of establishing a human presence on other planets to safeguard against existential threats like asteroids, supervolcanoes, and even human-made catastrophes. The warp drive Starship is a crucial step toward realizing this vision. By significantly cutting down the time and cost of space travel, it opens up unprecedented opportunities for exploration, colonization, and scientific discovery, allowing us to dream bigger, reach further, and redefine the limits of possibility. Conclusion. Elon Musk's unveiling of the new warp drive Starship isn't merely an announcement. It's a bold proclamation of our future. This groundbreaking technology signifies a leap beyond the confines of our solar system, setting humanity on a path to reach the stars. The potential impacts of this innovation are enormous, influencing everything from space exploration and travel to our understanding of the cosmos and our role within it. Despite the numerous questions and hurdles ahead, one thing is certain. We stand on the edge of a transformative era in space exploration. As we gaze into the future, the horizon of possibilities expands dramatically. The dream of interstellar travel, exploring new worlds, and uncovering cosmic mysteries is within our grasp. With visionaries like Elon Musk steering the course, the journey ahead promises to be extraordinary. So get ready, because the adventure is just beginning. The future is here, and it's traveling at the speed of light. Chapter 2. What the James Webb Telescope has seen beyond the dark ages. When even a Nobel Prize-winning physicist questions our current understanding of the universe, it signals that we are at a pivotal moment in astronomy. Adam Rees isn't alone in his confusion. The James Webb Telescope is increasingly uncovering new cosmic structures that defy established cosmological theories. How is it possible that galactic formations once deemed impossible are now being confirmed? What do these surprising discoveries mean for future research? And are our previous theories on the verge of being overturned? Answering such fundamental questions is complex. For instance, the seemingly straightforward question of how fast the universe is expanding delves into a deeper research mystery that has puzzled scientists for years. It is now well established that the universe has been expanding since its inception approximately 13.8 billion years ago. Consequently, galaxies are moving away from each other at a rate proportional to their distance. In other words, if Galaxy A is twice as far from Earth as Galaxy B, its distance from us is also increasing at twice the rate. Edwin Hubble was among the first to identify this relationship. To determine the rate at which two galaxies are receding from each other, one needs to know their distance and a constant by which this distance is multiplied, the so-called Hubble constant. And this is where things get particularly intricate. There has been a long-standing debate among experts regarding the true value of this constant. Historically, different measurements have yielded conflicting results, indicating that the outcomes are influenced by the measurement methods used. One approach relies on cosmic microwave background radiation, an almost uniform remnant from the early universe that supports the Big Bang theory. Using this method, we find the expansion rate of the universe to be about 67 kilometers per second per megaparsec. For context, a megaparsec equals 3.26 million light years, and 1 light year is approximately 9.46 trillion kilometers. However, when using Cepheid variables, specific stars with predictable brightness fluctuations, the expansion rate increases to 73 kilometers per second per megaparsec. This suggests that the universe is expanding more rapidly in our local vicinity, up to about 3 billion light years away, compared to the overall rate, which is puzzling. This discrepancy is known as the Hubble tension, and researchers have yet to provide a satisfactory explanation for this unexpected difference. The enigma has now come under the scrutiny of Adam Rees and the James Webb Telescope. Previously, some scientists hoped that the mystery of the universe's expansion rate might be attributed to a measurement error by the Hubble Space Telescope. Rees also aimed to determine if there were any inaccuracies in the Hubble data. In 2011, Rees, a physicist from Johns Hopkins University in Baltimore, was awarded the Nobel Prize in Physics alongside other researchers for their discovery of the accelerating expansion of the universe. To investigate further, Rees and his team utilized the James Webb Telescope to explore the causes behind the Hubble expansion measurements and to uncover any possible errors. But how exactly is the universe's expansion measured? The process involves the so-called cosmic distance ladder, where each stage builds upon the previous one, making any potential measurement error propagate through all stages. Cepheid variables, a key component of this method, are reliable only up to a certain distance. As the distance increases, the light from Cepheids blends with that of other stars, making them harder to measure accurately. Fortunately, the Webb telescope, with its 100-fold increase in power over Hubble, allows for deeper and more detailed observations of the universe's distant realms. The latest study published in the Astrophysical Journal Letters, however, presents a rather sobering update. The JWST surveyed the same regions as Hubble and found no discrepancies, leaving the issue of Hubble's tension unresolved. Rees offers a brief but profound explanation. It's possible we've misunderstood the nature of the universe. We now need to investigate whether something has been overlooked in our previous research and how to reconcile the universe's beginnings with its present state. This quest may challenge Einstein's theory of gravity. Adam Rees's team isn't the only group tackling the perplexing Hubble tension. Researchers from the universities of Bonn and St. Andrews are also exploring this enigma and have proposed a new potential explanation. They suggest that Earth resides within a bubble-shaped region of space with relatively low matter density. In contrast, the surrounding regions have higher matter density, and the gravitational forces from this denser matter pull the galaxies within the bubble towards its edges. This causes them to move away from us faster than expected. While this explanation is quite plausible, it introduces a new challenge. The standard cosmological model does not account for such bubbles or low-density regions. It assumes that matter is evenly distributed throughout space. This model is fundamentally based on Albert Einstein's theory of gravity, but it's possible that gravity operates differently in reality than Einstein's theory predicts. To address this, scientists have turned to a modified theory of gravity proposed by Israeli physicist Mordechai Milgram in the 1980s. Known as modified Newtonian dynamics, MOND, this theory, although not widely accepted, accurately predicts the existence of these bubbles. If Milgram's theory proves correct, many of the debates surrounding Hubble tension could be resolved, as the discrepancies would then be attributed to irregularities in matter distribution rather than inconsistencies in the expansion rate of the universe. The future will reveal whether this new approach gains acceptance and validation, but it also highlights the vast amount of knowledge yet to be uncovered about our cosmic past. The Universe Breakers. 1432. sometimes a single number can leave even the most seasoned astronomers astounded. The value 1432 represents the record redshift of the galaxy Jade's GS Z140, revealing that this gravitationally bound cluster of stars existed just 290 million years after the Big Bang. This discovery raises significant questions. How could such a galaxy be so bright and massive at such an early stage? Where did the necessary matter come from? Detected by Webb's near-infrared camera and IR cam, Jade's GS Z140 likely took 100 million years to reach its observed size. This galactic infant challenges almost all theoretical models and computer simulations of the early universe. It joins a select group of galaxies that the James Webb Telescope identified in early 2023, all of which were far more massive than expected. Despite existing when the universe was only 500 to 700 million years old, these galaxies were already comparable to today's Milky Way. Such findings contradict conventional cosmology, earning Jade's GS Z140 the nickname universe breakers among experts. These early galaxies, each containing over 10 billion solar masses of stars, with one potentially exceeding 100 billion solar masses, pose a significant challenge to our understanding. If even one of these galaxies is real, it would push our cosmological models to their limits. To account for their existence, the density of matter in the early universe might have been up to 5 times greater than current models suggest, or these galaxies could have formed in ways we have yet to understand. What does this mean in the broader context? Does it imply that we need to rewrite the history of the early universe and possibly the Big Bang Theory itself? New mysteries and old telescopes have emerged in our quest to understand galaxy evolution. According to current theories, dark matter initially collapsed into large clumps known as halos shortly after the Big Bang, within the first few hundred million years. The gravity from these halos then attracted normal matter, which eventually formed stars and galaxies. However, this process was gradual, leading to the slow formation of larger galaxies over time. In this framework, the galaxies observed by the Webb telescope seem implausible. Our previous theories didn't predict as many dark matter halos in the early universe as would be necessary for the formation of such large structures. Despite this, some experts, including Julian Munoz from the University of Texas at Austin, find it challenging to fully discard past research consensus. Munoz suggests that Webb's findings should be interpreted cautiously. He notes that if the early universe had 10 times more dark matter structures than previously thought, we would expect to see 10 times more galaxies in Webb's images. This should also be true for Hubble's data, but it isn't. Munoz and his team analyzed Hubble's galaxy counts across various brightness levels and attempted to adjust their model by adding more dark matter halos to match Webb's data. The issue was that this adjustment disrupted the consistency of Hubble's findings. So, which telescope should we rely on? While Webb is undoubtedly more advanced, having begun its scientific mission only in 2022, Hubble has been observing space for nearly 35 years. Munoz argues that, given the current situation, Hubble's extensive data might be more dependable. Therefore, it may be prudent to explore alternative explanations for the unusual early galaxies that don't require overhauling our entire understanding of the universe's evolution. These discoveries challenge conventional cosmology, earning Jade's GS Z140 the nickname universe breakers among scientists. These early galaxies, each with over 10 billion solar masses of stars, and one possibly exceeding 100 billion solar masses, pose a significant test to our current understanding. If just one of these galaxies is confirmed, it could push our cosmological models to their breaking point. To account for their existence, the early universe might have had up to 5 times more matter density than current models predict, or these galaxies might have formed in ways we don't yet comprehend. What does this imply for our broader understanding? Could it mean we need to revise the history of the early universe and possibly the Big Bang Theory itself? In our quest to unravel galaxy evolution, new discoveries and old telescopes have emerged. Current theories propose that dark matter collapsed into large clumps known as halos shortly after the Big Bang, within the first few hundred million years. These halos then attracted normal matter, eventually forming stars and galaxies. This process was gradual, leading to the slow formation of larger galaxies over time. According to this framework, the galaxies observed by the Webb telescope seem implausible. Our previous theories didn't anticipate as many dark matter halos in the early universe as would be required to form such massive structures. Nevertheless, some experts, including Julian Munoz from the University of Texas at Austin, find it difficult to completely dismiss past research. Munoz suggests that Webb's findings should be approached with caution. He points out that if the early universe had 10 times more dark matter structures than previously thought, we would expect to see 10 times more galaxies in Webb's images. This should also apply to Hubble's data, but it does not. Munoz and his team analyzed Hubble's galaxy counts across different brightness levels and tried to adjust their model by adding more dark matter halos to align with Webb's data. However, this adjustment disrupted the consistency of Hubble's findings. So, which telescope should we trust? While Webb is more advanced and started its scientific mission in 2022, Hubble has been observing space for nearly 35 years. Munoz argues that, given the current situation, Hubble's extensive data might be more reliable. Therefore, it may be wise to explore alternative explanations for the unusual early galaxies that don't necessitate a complete overhaul of our understanding of the universe's evolution. I hope you enjoyed our video. Don't forget to subscribe to our channel for more educational content like this. Thanks for watching.